If an as a series is convergent, also every term is positive, a positive series. And also the limit of an over a0 plus a1 plus all the way up to an is equal to 0. And we want to show that for this infinite power series that the convergence radius is just 1. So to prove this, first I'll show that the convergence radius is less than or equal to 1 first. Because here's my claim. R is less than or equal to 1. If otherwise, right? In other words, if R is bigger than 1, what's going to happen? Right? So, for example, R is right here. Right? So which means any point inside this open interval makes this infinite power series convergent. However, when x is equal to 1, we have exactly this numerical series given to be divergent. So that's a contradiction. Right? So really, my claim is correct. Then I'm going to claim the convergence radius is bigger than or equal to 1. Then I can draw the conclusion that the convergence radius is exactly 1. So why is that the case? Okay, so we're given this limit is equal to 1. I'll just denote Sn is a0 plus all the way up to an minus 1 plus an. So therefore Sn minus 1 is equal to a0 all the way to an minus 1. So I can express an as Sn minus Sn minus 1. So in other words, the given condition is just the limit of Sn minus Sn minus 1 over the bottom is exactly Sn is equal to 0. So in other words, the limit of Sn over Sn is just 1. Right? So 1 minus Sn minus 1 over Sn is 0. So the limit of Sn minus 1 over Sn is exactly 1. Right? So how is this useful? So I'll just denote Bn as Sn minus 1 over Sn. In other words, limit of Bn is 1. So this is helpful, because next I'm going to claim that the limit of the nth root of B1 times B2 all the way up to Bn is also 1. In other words, the limit of the geometric average is also 1. So what I've done so far is I've proven R is less than or equal to 1. Then I'm going to claim R is bigger than or equal to 1. Then I've reached the conclusion that the Bn denote Sn minus 1 over Sn. Sn is the partial sum of a0 plus all the way up to an. Right, we've shown that this limit is equal to 1. I'm going to show this limit, geometric mean, is also equal to 1, the limit. First of all, I'll show that, let's note Bn is also positive. Right? So if the limit of Bn is 0 instead of 1, then I'm going to show that the limit of the arithmetic mean is also 0. Here's how. So given any epsilon bigger than 0, can we find a capital N So that when little n is bigger than capital N, this absolute value is less than epsilon. Right? So this absolute value, I don't need absolute because it's already positive. Right? So B1, Bn can be written as B1 all the way up to B capital N. I'll explain what this means. B capital N plus 1 Bn over N. Okay? So this capital N comes from this limit, because this limit is 0. So which means there exists a capital N, so that when little n is bigger than capital N, this absolute value, I don't need absolute value because it's already positive, can be less than half of epsilon. Right, this is achievable. Right, so that every term from this term is less than half of epsilon. Right? So this is less than. First of all, since Bn has a limit, therefore Bn is bounded. Right? Bounded, so bounded by capital M, m bigger than 0. So every one bounded by m. So capital N times capital M over little n plus little n half epsilon all the way half epsilon. And so capital N, capital M is fixed. N approaches infinity. This can be small enough, smaller than half epsilon. Right, when n is bigger than capital N1. And this is how many? Right? So n minus capital N, this many, less than half epsilon. N minus capital N over n is smaller than 1, so it's smaller than half epsilon. Epsilon. Right? So as long as little n is bigger than this capital N and this capital N1, in other words, bigger than maximum of capital N and capital N1, I call that capital N2. Right? Then the limit, then this absolute value, right, this can be smaller than epsilon. Right? Limit is really equal. Now I've proven my claim. As long as limit of Bn is equal to 0, their arithmetic mean also equal to 0. So right now Bn limit is equal to 1. For example, equal to B in general. What happens is now that Bn minus B, this limit is equal to 0. Call that Cn. I can apply this result, right? So the limit of C1 all the way to Cn over n. This limit is equal to 0, right? In other words, C1 is B1 minus B. B2 minus B, B3 minus B, all the way to Bn minus B over n is equal to 0. But right now, this is n many B's, right? B1, Bn minus n times B over n. This limit is 0. Therefore, move this minus B onto right-hand side. Limit b1, bn equal to b. Okay, so far we've shown as long as the limit of bn is equal to any number b, then the limit of their arithmetic mean is also b. In this case, b is equal to 1. Now, I want to prove this claim. Right? Geometric mean is also tending towards 1. Here's why. So the AMG harmonic mean less than or equal to geometric mean. Harmonic mean less than or equal to geometric mean less than or equal to arithmetic mean. Right? Now, because limit of bn equal to b, limit 1 over bn equal to 1 over b. Right? So this so first of all, this limit is equal to b. This is tending towards what? So if n, so it's a reciprocal. Reciprocal is a arithmetic mean of those numbers. Right? So again, applying this result, right? Except the limit of 1 over bn is 1 over b, obviously, right? So tending towards 1 over b, right? Their arithmetic mean tending toward the same limit, no problem. So it's reciprocal, tending towards b. So really, squeeze theory also tending towards b, right? No problem. In this case, it's 1. So like I said, how is this going to help us, right? So it's the geometric mean b1 times b2 all the way to bn nth root is equal to nth root. b1 is S0 over S1. B2 is S1 over S2. All the way. Bn is Sn minus 1 over Sn. Right? So I can cancel out the majority of the terms. Right? This term. S2, S2. And this S minus 1 cancel with the previous. So this and this, only ones left. S naught over Sn, nth root, tending towards 1. Good. And we also know that the limit of like Bn is bigger than 1, so this is legitimate, right? Positive, no problem. And S naught is a fixed positive number. This limit is well known. So, combined with this limit, we immediately know the limit of nth root of Sn is also 1. How is this going to help? So how is this going to help us? Well, first of all, we know An is no larger than Sn. An is just a term out of this partial sum. So if we take limit supremum of nth root of an, then that's going to be no larger than the limit supremum of nth root of Sn. But it already has a limit, right? So convergence radius is equal to 1 over lim sup nth root of absolute value. It's already positive, bigger than or equal to 1. Right? So yeah, I've proven convergence radius bigger than or equal to 1. Combined with the convergence radius is less than or equal to 1. So convergence radius is really 1.